Okay, one of the most important and certainly the most well-known externalities of human energy use is climate change, which more accurately would be called global heating. You've all heard about climate change. This video will present some new and important perspectives that you might not have thought about before. Most of you have probably had the basics of global heating. Here's a quick review. Fossil carbon in oil, coal, and gas are geologic stores of past solar energy that we're re-injecting into the planetary system millions of times faster than they were sequestered. Climate change is simply a change in the planetary energy balance. 88% of human CO2 emissions are related to the burning of this ancient sunlight that accumulated over hundreds of millions of years. The other 12% is from our land use changes, mostly removing forests and releasing their carbon. About 30% of the total of these emissions is absorbed by land and forests. Another 24% is absorbed by the oceans. The remaining 46% stays in the atmosphere, where it functions as a greenhouse gas. As most of you know by now, certain gases, water vapor, nitrous oxide, methane, and carbon dioxide, change the chemical composition of the atmosphere and cause heat to be trapped. This is called the greenhouse effect. Under most circumstances, it is a very good thing. Without the greenhouse effect, Earth would be negative 19 degrees Celsius instead of positive 15. Okay, here's how it works. There are 342 watts per square meter of incoming solar irradiance coming to the Earth from the sun. 77 watts of this is reflected from the atmosphere and clouds back into space. 67 watts is absorbed by the atmosphere and clouds. 30 watts is reflected from the Earth's surface, leaving 168 watts of heat absorbed per square meter of Earth's surface. Scientists measure how much impact human greenhouse gases have by looking at their radiative forcing, or how much additional energy per square meter they force into the planetary system. The biggest of these forcings is CO2, but there's also methane, ozone, and nitrous oxide. The net impact of all current human-related forcings equates to about 1.7 watts per square meter. This is small relative to the entire heat system, but meaningful because the Earth's environment is a complex adaptive system and is sensitive to abrupt or large changes. We now know that CO2 in the atmosphere is higher than at any time in the last 500,000 years, which stands to reason given that we're re-injecting millions of years of stored carbon back into the atmosphere every decade or so. But as you can see in this graphic, neither CO2 nor global temperatures nor sea level rise have been stable. The top panel in green shows CO2 fluctuations over the past 450,000 years. The middle panel in red shows global temperature in Celsius. Note there were several times that temperature changed by 8 to 10 degrees Celsius in not too long a time frame. The bottom panel shows global sea levels relative to today. Sea level today is already some 400 feet higher than around 20,000 years ago. If we zoom in on that red panel, on global temperature to the very recent past in the above graph, we can see that the climate we've been familiar with during our development as a species has been abnormally stable for the past 10,000 years or so, which at least partially explains why our great-grandsters developed agriculture at around the same time temperatures stabilized in at least 5 places on Earth. Due to the greenhouse gases we've already emitted, it's extremely likely we're headed for a warmer planet than this 10,000 years of the Neolithic. But how much warmer, and what are the risks? This topic could be a 5-hour video series itself, or even 50 hours, but let's take a quick look at some context. First, really big picture. Since the rise of multicellular life, there have been 5 major extinction events, and many minor ones. An extinction event is where a large percentage of Earth's families and taxa are suddenly, in geologic terms, no longer found in the fossil record. Many of these prior events, where large extinctions occurred at the genus level, were correlated with large pulses of carbon dioxide from volcanism. There were times in Earth's history where massive volcanic activity lasted for tens of thousands of years, had lava flows as long as 1,000 miles, and lakes of lava 500 feet deep. These were called igneous provinces. This created widespread venting of great amounts of CO2 and methane into the atmosphere. As you might guess, this usually didn't end well. The blue spikes in the graph here show the percentage of genus-level extinctions over the past 300 million years. The red lines were these known large igneous provinces where large long-term volcanic activity had occurred. The biggest mass extinction in Earth's history, the Permian-Triassic at 250 million years ago, where 96% of all species alive at the time were lost, was due to massive volcanic activity filling the air with CO2 and enabling all kinds of methane-producing bacteria. Other lesser extinctions followed, and many of them were linked to CO2 pulses due to volcanism. So, today, our industry, cars, and removal of forests are functioning similar to volcanic provinces of old. But the amount of CO2 that civilization is releasing is not approaching the massive amount that the volcanic activity from the Deccan Traps created in India over the course of 30,000 or more years. But the increase from human activity is occurring much, much faster. On the other hand, we are starting from, at least geologically, one of the lowest CO2 regimes of the last 500 million years, shown as the black line in this graphic. Many of you are already aware that the years you've been alive are all the warmest years of the past 150 years, and trending higher. But what does this imply about the future? What do we know, and what can we infer? We know higher CO2 regimes will result in higher average temperatures, especially near the poles, more heat waves, more standard deviation of floods and droughts, more need for water, and the agricultural impacts mostly negative, even though some crops like rice and soybeans are expected to do better in warmer planet. I'll review the risks to oceans a bit later. As you might guess, the impacts get worse the higher the ultimate temperature is. At 2 degrees of warming, Celsius, heavy rainfall events will increase in intensity by 7% relative to a 5% expected increase if we stop at 1.5 degrees Celsius. Freshwater availability in, for example, the Mediterranean will decline by 17% at 2 degrees Celsius versus a 9% decline at 1.5. So, how likely are these future climate impacts and how bad might it get? As we're aware from the human cognitive bias section, pretty much everyone has an opinion. In your own zip code, you can probably find someone who thinks humans will be extinct in the next 20 years from climate, as well as someone who thinks climate is a socialist scam and we're headed for an imminent ice age. The good news is we have tens of thousands of scientists working full-time on quantifying these issues, and the models are getting much better. But they're still models, trying to model a complex system. Okay, recall that human emissions are currently at around 1.7 watts per square meter of additional radiative forcing to the planetary energy balance. Climate scientists have created scenarios of future emissions and natural feedbacks called representative concentration pathways, or RCP scenarios for short. They range from a best case outcome of RCP 2.6, where we stabilize at 2.6 watts per square meter, all the way to RCP 8.5, where the human impact on global energy balance goes from 1.7 today to 8.5 by the year 2100, which, if it occurred, would result in CO2 of over 1,000 parts per million. And I'll point out the obvious that is often missed. The physical trends from these models don't magically stop in 2100. Only the models do. The answer to which of these paths we're on and which will end up being the reality depends greatly on what the future of fossil carbon availability and economic growth is. In all 4, and there are only 4, of the RCP scenarios, economic output for the world in 2100 is predicted to be considerably higher than today's. And this is powered by amounts of coal, oil, and natural gas that don't yet exist as reserves. Under that RCP 8.5 scenario, the average human is 8 times richer in physical terms in 2100 than today. Most of the really scary literature you read on the internet solely refers to this RCP 8.5 scenario, which assumes that we continue business as usual, economic growth using increasing amounts of fossil carbon throughout this century. The good news, if you could call it that, is that these scenarios were not designed by climate scientists, but by economists who view the world with a money in, energy out worldview, instead of an energy and materials in, energy and materials out worldview articulated in those energy videos you just watched. For instance, the RCP 8.5 scenario projects in the year 2100 we'll use technology to turn coal into liquid fuel at a scale generating 200 million barrels of oil per day, when all the real oil itself today isn't even at 100 million barrels. This isn't well known, but the designers of the RCP scenarios started with targets for radiative forcings and then created economic scenarios that would produce them, not the other way around. I'm personally very worried about climate and especially oceans after I'm dead and gone. But my personal view is that we don't remotely have the amount of affordable carbon to meet either the RCP 6 or RCP 8.5 scenarios. However, the current narrative in the popular press and talk show circuit make those scenarios seem inevitable. Okay, here is the most dense graph of this entire video series, but I'm going to risk your eyes glazing over to make a point. The left axis on this graph shows the projected temperature change relative to 1850-1900 baseline. The bottom axis shows the cumulative CO2 emissions from human impact through 2017 in the purple line and projected forward. This image is from the latest 2018 IPCC special report on the 1.5 degrees Celsius scenario. The red line in this image is that RCP 8.5 high emission scenario I mentioned, which shows a linear increase in fossil carbon consumption and impact throughout this century. A lot of the people who are very concerned about climate change think we've been following this red line and talk about future climate as if we continue to following this line. And rightly so to be concerned, because if we were following that line, we'd be in a hell of a lot of trouble. But all the science that was part of this latest IPCC report shows we're following much closer to the purple line, and future scenarios will likely be in the purple envelope. These scenarios continue to assume abundant fossil carbon availability and growth, which I'm not so certain about. To arrive confidently in the 2 degree Celsius area of this plot would take another 40 to 50 years of CO2 emissions at the current rate from fossil carbon and land use. I present this to show 2 degrees Celsius, despite much commentary in the news to the contrary, is not yet a certainty. Okay, so there's a great deal we know about global heating and a great deal of both risk and uncertainty. The previous confusing graph does not mean that we are not creating significant risks of longer-term Earth system carbon dioxide effects from our impacts on the biosphere. It does mean that many of the high emission scenarios we hear in the environmental media are based on unlikely economic growth assumptions. But CO2 doesn't just impact temperature and climate. The oceans, for most people, are out of sight, out of mind. There are now numerous systemic risks as a result of human energy use which involve the oceans. Here's a whirlwind summary. Recall this graph of the CO2 flux per year over time. Look at the dark blue. Since the beginning of the Industrial Revolution, about 250 years ago, the oceans have absorbed a third to a half of the CO2 released into Earth's atmosphere by human activities. Currently, 24% of each year's human emissions ends up in the oceans, which as a result are getting warmer, more acidic, and as a result losing oxygen. Let's take a brief look at the risks to oceans from the perspective of the metabolism of the human ecosystem. Ocean risk number 1, sea level rise. Sea level today is around 120 meters higher than it was 20,000 years ago due to the end of the Ice Age, but it's still over 30 meters lower than during very warm periods. If the climate does warm by 2 degrees Celsius, the ocean levels are expected to rise 0.5 to 1 meter this century, though higher increases are likely over longer horizons. The above graph shows global coastlines under a hypothetical scenario if the entire Greenland ice sheet melted under positive feedbacks. Many of the world's seaports would be inundated at even a 1 meter sea level rise. Sea level rise impact goes much further inland than the water itself does. The salinity affects agricultural land well inland. This will be very important in places like Bangladesh, where much of their land growing crops is at low elevation. Ocean risk number 2, warming. Because seawater has absorbed much of the carbon to date, up to 90% of the warming resulting from human emissions has gone into the oceans. Warming poses risks to sea life. Coral species, for example, cannot withstand extended hot periods. They start to die off, which diminishes reef diversity. Ocean warming also provides more heat energy, which makes hurricanes more intense. Ocean risk number 3, acidification. During the Industrial Revolution, seawater has experienced a 30% increase in acidity. This increase is approximately 100 times more rapid than at any other time during the most recent 650,000 years. Pteropods are small, calcifying, shelled organisms that live as zooplankton in the water column and are important prey species for many fish. An increase in ocean acidity can break down their calcium carbonate shell, ultimately leaving fish, cetaceans, and other creatures up the marine food web at risk. Ocean risk number 4, circulation. The oceans have thousands of currents that act like a giant conveyor belt, transporting heat from the tropics to higher latitudes. As warm water from the tropics flows towards the poles in wind-driven currents near the surface, it cools, becoming denser and heavier, and it eventually sinks. It then begins a long, slow journey deep in the ocean, flowing back toward the equator. This thermohaline circulation draws greenhouse gases and heat deep into the ocean, thus alleviating the early effects of CO2 emissions by human. This thermohaline circulation draws greenhouse gases and heat deep into the ocean, thus alleviating the early effects of CO2 emissions. If the ocean warms, this circulation slows down, thus creating a positive feedback in the sense it becomes less effective at drawing CO2 and heat out of the atmosphere. The Atlantic Ocean circulation has already slowed by about 15% since the middle of the last century. Ocean risk number 5, oxygen. Global oxygen concentrations are decreasing due to fossil fuel burning because we're consuming O2 at a rate of 1,000 times faster than pre-industrial times. Oxygen levels have dropped by 0.1% in the last century, so this isn't overly worrisome on human timescales. However, there has been a 2% decline in ocean oxygen content during the last 50 years. Warmer water affects the ability to dissolve and hold oxygen. Warming also impacts ocean currents, which transfer oxygenated water between regions. This 2% drop is an average, so shallow ocean areas near coastlines are much warmer, which has impacts on seagrasses, which are the home for baby fishes and other sea creatures. At the extreme end of some longer-term risks, some of Earth's extinctions were linked to times when warming at high latitudes stopped this exchange of oxygen to the deep oceans, and Earth's seas and oceans eventually became stratified with areas of little to no oxygen called anoxia. Lots of unknown risks and potential positive feedbacks are at play here. Okay, a brief summary of the climate and ocean section. First point, many of the impacts on Earth's environment are not included in our price system. They're external to our price system. They're shifted cost to the environmental commons. Point number 2, the direct byproducts from human energy use are heat-trapping gases, methane, carbon dioxide. Point number 3, given the speed of human emissions, we are now in uncharted territory. Some amount of warming, perhaps 1.5 degrees Celsius, is now very likely. Point number 4, At the same time, many of the Armageddon climate scenarios that are frequently in the news are unlikely because the affordability of that scale and level of oil, gas, and especially coal use is highly questionable. Our general energy blindness makes us overestimate climate impacts and correspondingly underestimate economic risks. More on that in upcoming video. Point number 5, the oceans are not often highlighted in the media, but have been bearing the brunt of human emissions, and those risks are important. Point number 6, if you consider the human system as one that uses energy and grows, we should consider climate change and ocean-related risks as symptoms of the problem, not the problems themselves.